Hello, folks. In this lecture, we're going to continue working with Lewis structures as we develop our understanding of covalent bonding within polyatomic molecules and ions. So let's get to it. Let's do a molecular system with more than two atoms, ammonia, NH3. Nitrogen brings 5 valence electrons to the system, and each hydrogen atom brings a single electron. The total number of electrons is 8. The most symmetric arrangement of the atoms is to have the nitrogen atom in the center with the 3 hydrogen atoms scattered about it, since hydrogen atoms are not usually central atoms. We now place 2 electrons between the nitrogen and each hydrogen, leaving us with 2 electrons to satisfy each of the atoms. The hydrogens have 2 electrons shared in the bonds, and that's all they need. Placing 2 electrons on the nitrogen give it 8. We have a solution. So each NH bond is a single bond, and we have a single lone pair of electrons on the nitrogen. Perfect. Now let's do one more. CH2O is an interesting organic molecule called formaldehyde. Carbon brings 4 valence electrons. The oxygen 6 and the hydrogen atoms bring 1 electron each to the molecule for a total of 12 electrons. So how do we arrange this bad boy? Well, typically in carbon, hydrogen, oxygen, organic type molecules, the carbon will be the central atom. All you needed, huh? Another rule. But anyway, in this system, the carbon is central, and the oxygen and hydrogen atoms are placed around it. We place 2 electrons in each bond that will be the 6 electrons used in bonding. And the hydrogen atoms are already happy with 2 electrons in the bonds, leaving us with 6 electrons to spread between the carbon and the oxygen atoms. So we come up short on electrons. We can't place a double bond between the carbon and the hydrogen atoms because that'll give too many electrons to the hydrogens. So we'll place a double bond for a total of 4 electrons between the carbon and the oxygen. We now have a total of 8 electrons in bonding, leaving us with 4 electrons which are placed around the oxygen atom, since the carbon atom already has an octet when including all of its bonded electrons. So everyone's noble. We win. We have 4 bonds total and 2 lone pairs on the oxygen atom. Let's draw an important compound that exists in our atmosphere. The molecule O3, which has a formal name of trioxygen, but which is better known as ozone. O3 is a pollutant, very reactive and dangerous for us here at the surface of our planet, but it is a critical component in the upper atmosphere where it's our main protector against the dangerous UV light pounding us from the sun. It's this UV that's the main culprit in giving us skin cancers. Now, each oxygen brings 6 electrons to the party for a total of 18 electrons. The atoms are all identical, so the basic arrangement is just to line them up. We place a couple of electrons between the bonds, leaving us with 14 electrons to scatter amongst the other atoms. We come up short, so we will place 2 more electrons between the oxygen 1 and oxygen 2 atoms, creating a double bond. Now we have 12 electrons to create oxygen octets. This works. The thing is, we would have gotten an equally valid structure if we had created the double bond between the oxygen 2 and 3 atoms. Both structures are equally valid Lewis structures. The result is that the electrons involved in the bonding of ozone are delocalized with the electron density sloshing between these 2 Lewis structures. It's very common to denote this resonance with a double arrow between the Lewis structures. A shorthand way of describing the Lewis structure and the resonance is to draw the partial double bond between the oxygen atoms with a dashed line. It's common to say that the bond between each of the oxygen atoms is not a double bond, but a bond and a half. That being said, it's harder to describe the lone pairs this way, so a correct way of describing the resonance for you, at least until you get more familiar with the chemistry, is to draw each Lewis structure and draw the resonance arrows. Remember though, resonance is good. The delocalization of the electronic density helps stabilize a molecular system and is a good thing for the molecule. Now let's consider the question of polyatomic ions. These are interesting cases. Now we know that ferrous or iron 2 carbonate is an ionic compound, but the polyatomic anion, the carbonate CO3 2-, is made up of a carbon-oxygen atom that form covalent bonds. You can check these using the Kettelard triangle. Now we want to draw the Lewis structure of just the CO3 2- polyatomic anion. The carbon atom has 4 valence electrons, and the 3 oxygen atoms bring 6 times 3 electrons to the bonding, so we have a total of 22 electrons so far. The charge of the polyatomic ion is -2, so that adds 2 more electrons to this molecular system, giving us a total of 24 electrons in this structure. The carbon is the central atom surrounded by the 3 oxygen atoms. Beginning as always with single bonds between the carbon and each oxygen leaves us with 18 electrons to scatter among the atoms. We come up 2 electrons short. So a double bond is placed between the carbon and one of the oxygens, fixing our problem. But there will be 3 different structures possible, producing a nice resonance between them. We place our brackets around the ion and place our 2- superscript on the system. The final Lewis resonance structure for the iron 2 carbonate system is shown. Like everything we tried to explain with simple ideas, exceptions to the Lewis rules of producing structures do exist. Remember, the Lewis ideas are at best a first approximation to the bonding. Now here are some of the more well-known exceptions to the Lewis octet rules. Incomplete octet. The most classic of these exceptions involves the boron atom that routinely will be stable enough just having 6 electrons around it. Shown is the boron trifluoride compound. The next exception is odd electron systems, molecular compounds with an odd number of valence electrons in total, cannot produce perfect octets on every atom. Inevitably, there will be an unpaired electron in the structure. These types of systems can form what we call free radicals, and as would be expected, can be relatively unstable. The classic example is nitrogen monoxide. Nitrogen brings 5 electrons to the molecule, and the oxygen 6 for a total of 11 valence electrons. Since we can't get to an octet on both atoms simultaneously, we envision a weird type of resonance between 2 possible structures, which on average would give the nitrogen and oxygen atoms something close to an octet, stabilizing the molecule. Expanded octet. Now these are systems where the central atom has greater than 8 valence electrons surrounding it. These are more common with elements in periods 3 and higher, which have D and F orbitals available, and a variety of valence orbital combinations that are possible to them. Pictured is the PCl5 phosphorus pentachloride compound. Notice the expanded octet around the phosphorus on this system. All right. We now have a tool given to us by Lewis that we can use to give us an idea of the molecular electronic structure for ionically and covalently bonded systems. Now, all that's left now is to fine-tune our Lewis structures and figure out what these molecular systems might look like in 3D. That's coming up, so I'll see you soon.